There we go. Now I'm recording. Sorry. So we have 6 people at a party, and we've chosen A out, and we've said that a pair of people is either acquainted or not. If they're acquainted, we could draw a line, or if they're not acquainted, we could draw a line. That's our choice, an edge that connects them. So what I said is, of these 5 people, then a minimum of 3 of them are acquainted with A, or if that's not true, then a minimum of 3 of them are not acquainted with A. And so whichever it is, I'm going to use that relationship as the one that I'm representing with a line here. So let's suppose, because it could go either way, but it's easier to say they're acquainted, let's assume that A is acquainted to B, C, and D. It doesn't matter which 3 I pick. B, C, and D. So now we have 2 choices with B, C, and D. Either B, C, and D, none of them know each other, no acquaintances, in which case there's our 3 people. So if B, C, and D don't know each other, no pair of them know each other, then B, C, D is our set of 3 people that didn't know each other. That's pretty easy. And so otherwise, one or more of B, C, and D know each other. So we could get the edge BC, we could get the edge BD, or we could get the edge CD. If I color any of those edges, for instance, BC, then I get a triangle in my original graph, so I get that A, B, and C are mutual acquaintances. And the same is true if instead I said, well, maybe it's just B and D that know each other, then I get that triangle of mutual acquaintances. Or if I said C and D know each other, then I get the triangle ACD. In either case, I get a triangle of mutual acquaintances, which I'm not even going to try to spell today. All right, so that is the kind of beginning Ramsey theory problem. This was a relatively common puzzle problem, and that's really how a lot of these combinatorics ideas got started. And so what we say here is that this is the language that our book is going to use in its common language. 6 has the Ramsey 3-3 property. I'm going to explain that in just a second. Show off. I got the C and the Q in the right order at least. Let's see. So 6 has the Ramsey 3-3 property, which in order to see that language, oh, our book says the 3-3 Ramsey property. So the Ramsey property is this notion of either a thing happens or a different thing happens. And a number having the property means that any group of 6 people at the party will have the property that either 3 are mutual acquaintances in this case, or 3 are have never met. And I mean, it could be both, right? It could be the case that A, B, and D are mutual acquaintances and C, E, and F have never met. We're not worried about that. When I say either, I don't mean it exclusively in any way, shape, or form. We have, this is a symmetric Ramsey number because I chose the same 3 for 3 are mutually acquainted or 3 have never met. There is a number that of people that would guarantee me that either 3 are mutually acquainted or 4 have never met, and so on. 6 turns out to be the Ramsey 3-3 number. I'm going to make this claim right now. So we say the Ramsey 3-3 number is 6 because 6 is the minimum of all numbers with the 3-3 Ramsey property. That should be capitalized. So that's making 2 claims there. First, that 6 has the Ramsey 3-3 property. Yeah, it's at least 3. At least 3. That we're looking. So what Ramsey theory is about is a certain minimal order that comes out of the noise. So we can have any random set, and if it is of a certain size, then we get a certain, we're guaranteed by Ramsey theory, a certain minimal order. And so any set of, let me phrase it here in the way we're going to talk about it in chapter 3, the graph theory chapter, is any graph with 6 nodes either has a complete subgraph on 3 nodes or an empty subgraph on 3 nodes. So of course, if it has a complete subgraph on 5 nodes or 6 nodes, it would have a complete subgraph on 3 nodes, and that would be enough to satisfy the property. So the dual claim that the Ramsey 3-3 number is 6, we've proved part of it here, just with this simple diagram, is that Ramsey 3-3 cannot be greater than 6. We've shown that 6 works, so since the Ramsey 3-3 number is the minimum of all of them, it can't be more than 6 if 6 works. Because if 6 nodes guarantees the Ramsey 3-3 property, then of course 7 nodes, you have 6 nodes. So that guarantees the Ramsey 3-3 property. Note that it is the number that has the Ramsey property, not the individual graph. So we don't say a graph has the Ramsey 3-3 property. We say 6 has the Ramsey 3-3 property because that's saying that every graph with 6 nodes satisfies that property. And so, so the other side of that is we have to show that 6 is not too big, right? That 5 doesn't work. And so how would we show that 5 doesn't work? Let me spell out the definition a little bit better. Let's jump over to page 225, and I actually, let's see. I think I'm going to use the theorem 331 statement of the Ramsey property. So I'm going to use this as my definition instead of as a theorem. So there's a bunch of theorems here because there are like dozens of different ways to say the exact same thing. So you make one of them the definition, and then all of the equivalent statements are theorems. I'm choosing this one to be my definitional statement. A number n has the PQ Ramsey property if and only if for every graph G of n nodes, either G has a clique of P nodes or an independent set of Q nodes. So a number n has the PQ Ramsey property if and only if. So P and Q could be different numbers. What we've said down here is 6 has the 3,3 property because any graph with 6 nodes contains a clique of size 3. Remember, clique is just another word for complete subgraph, or an independent set of Q nodes. And an independent set, remember, is you get nodes with, I think I've been calling that an empty subgraph all semester long. So an independent set would be an empty subgraph. And in that case, we say, let's see, RPQ equals n if n is the minimum integer such that n has the PQ Ramsey property. So this notion of a clique of P nodes or an independent set of Q nodes is a really nice way to look at it. I'm not going to write out every other version, but I want to highlight a couple of them. So one of the other nice ways to look at this is to look at G complement, where G complement has the same node set, but the opposite, colloquially speaking, edge set. So any edge that is in G is not in G complement, and any edge that is not in G must be in G complement. So to be really, if we have that 3 vertex graph, then that would be G complement, for instance. And so if I look at it that way, I can say that N has the Ramsey property, the PQ Ramsey property, if either G has a clique of P nodes or G complement has a clique of Q nodes, because an empty graph in Q nodes is the same as a clique, or shouldn't say a clique in that case, a complete graph in the complement of that. Right, if I have that as part of my graph, then in the complement I will have that. Part of what makes the 3,3 Ramsey number fairly easy to work with is because a complete subgraph in 3 vertices is the same as a cycle graph in 3 vertices. I'm not going to overwhelm you guys with different papers that you can look at, but if you get curious, there are a lot of papers about this topic on the freely available combinatorics.org, the electronic journal of combinatorics. It is, as it says, an electronic journal, and it is free. And one of the most important repositories of graph theory information is there. Let me see if I can share my screen with you and show you. It's this paper here, which I've flipped ahead to page 4. Let me get to the top real quick. So this paper is not a paper in and of its own right, but it's a compilation of all of the known information out there about small Ramsey numbers. And small Ramsey numbers means, you know, P and Q are not more than like 20. And it is huge, and it gets updated every few years. As far as I can tell, 2017 was the last time it was updated. And so I wanted to show you some of these Ramsey numbers here. So we see that the Ramsey number 33 is 6, which I've claimed. I haven't finished proving that yet, but I did claim it. And we know the Ramsey 44 number is 18. But then here when we get to the 55 Ramsey number, we have a lower bound of 43 and an upper bound of 48. The 48 actually happened within the last few years. I think that may have been what prompted this revision in 2017, actually. What's going on is that this means that in order to guarantee that a graph has a clique of 5 nodes, or its complement has a clique of 5 nodes, it needs to be somewhere between 43 and 48 node graph. And we're not sure which, because, well, a 43 node graph has a lot of possibilities. And if we are to brute force through this, this is one of the NPs. I don't recall which one. Because, well, actually, I'll get to that in a second. Anyway, there's a lot to hunt through. So to try to bump the lower bound, what we actually have to do is search through, if you think about it, like if we wanted to brute force it, we'd have to search through all of the graphs on 43 nodes. And that is a large number of graphs. Now, many of them are isomorphic to each other, but the isomorphism problem is itself not an easy problem. To determine whether two graphs are isomorphic is up in the NP classification, if I remember correctly. So knowing whether or not we can filter out some of the graphs is just as hard as sorting through all of them. So if we sifted through all of the graphs on 43 nodes and we found one that didn't satisfy that 5-5 Ramsey property, we found one and we're like, hey, this doesn't have a clique in 5 nodes, and when I take its complement, neither does that, then we would have shown that that minimum actually needs to be bumped up to 44. In order to play with the upper bound of 48, there are some estimations out there that is how they get these, and they're working using theoretical mathematics to kind of lower the upper bounds. So one of the things I find interesting about Ramsey theory is that to improve the lower bounds for these, we're really looking at, can we write a better algorithm? Can we arrive there in less than crazy exponential time by, let's call it, clever guessing? That's one of my favorite phrases here. If we can clever guess our way past, through the thicket of possibilities, but that's really an algorithm issue. One of the things that people have tried is genetic algorithms to take some graphs on 42 nodes that don't satisfy the 5-5 property, and then to take them and bump them up to a 43 node graph. Or actually, no, I'm sorry, that's not what they did. They started with a 43 node graph that had a relatively small number of cliques of 5 vertices, and so did its complement. And then they randomly perturbed the graph so that it was different, right? They created child graphs from those I forget how many they seeded with originally. But you know, something maybe 10 graphs with a relatively small number of clicks of size 5, or maybe it was whose largest click was less than 8, or something that was close to 5. Like, I can't recall exactly how they did it, and I'm sure there's been people that played with it in different ways. It's been a couple of years since I looked at the paper. I think they counted the number of clicks of size 5 in the paper I read, and so that was their metric by which they evaluated the child graphs. So they created random graphs using, I believe it was, I apologize, comp sci is not my field, but they used the version of the genetic algorithm that is like asexual reproduction. So they would take an individual parent and randomly perturb it and make like 5 kids, and then they would do that for all of their seed, and then they would only keep the best 10 or whatever and repeat the process. It was not a fruitful search. That I'm surprised the paper even got published. As a matter of fact, I think the paper is not actually published so much as somebody wrote up their results on like their own personal website or blog or something, because there was not a fruitful search. But it gives you an idea of the kind of things people are trying. So to attack these lower bounds, we need good computer scientists. To attack these upper bounds, we need good mathematicians. These sorts of things. Here, let me share a different screen with you. I'm not ready to show you that. I'm sorry. I keep forgetting I haven't told you enough to actually get there yet. Let's go ahead and finish establishing that R33 equals 6. So we've shown that R33 is less than or equal to 6, right? By showing that every graph on 6 nodes contains a click of size 3 or an empty subgraph of size 3. And by the way, I will waffle right through those descriptions. Let me give you the third one. I said click an independent set. I said G and G complement both, or either one contains a click. The other one that is kind of interesting is that if we do an edge coloring, any edge coloring of K6 will have either 3 red edges or 3 blue edges, assuming those are the 2 colors you use, of course. That is an interesting one because it generalizes up. And so we could talk about the R333, which is, what if we did a 3 edge coloring? Then how many nodes would we need to guarantee that one of our edge colorings had a 3-edge triangle in it? Anyway, I think I said that wrong. So I should have said a red click of size 3 or a blue click of size 3. And so then this would be like red, blue, or green clicks of size 3. So that's, I don't know what this symbol is here. I don't remember what I was writing when I said that. So those are 2 kind of different ideas. Anyway, let's show that this works. Let's let G equal K5. So K5 could look like this, right? I'm sorry, not K5. Z5 or C5, depending on whether we're following our book's notation or the notation I've been using in class more often. So there's one way to write C5, and here is the complement of that. And you'll notice that neither of those contains a triangle. So if this is G, then this is G complement. G does not contain a click on 3 vertices, and neither does G complement. Yeah, the online integer sequences contains every sequence you can imagine. Are those the symmetric Ramsey numbers, or does it give it as a binary, not a binary, yeah, a two variable sequence? Two variable sequence makes sense. The main issue with that is what I started to get at here, is that one of the ways that we've played with Ramsey theory, because making these numbers larger is harder to find actual numbers. Enterprising mathematicians and computer scientists have just allowed there to be more numbers, and we can get some good results there. So here, this shows that 5 does not have the Ramsey 3-3 property. Because in order to show that an integer doesn't have the property, all we have to do is find one graph and its complement that sort of fail that test. So how about this? How about corollary 329? The Ramsey P2 number equals P. See how we would show that. And the book has a little almost one-line proof, but it really only goes one direction, because the other half is left to you guys in the homework. So to show that, we want to show two things. RP2 is less than or equal to P, and RP2 is greater than or equal to P. It's really easiest to split these into two cases. To get there all in one go is hard. So this is the one that our book shows, and it really makes sense. If you have a graph, if G has P vertices, you have two choices. G equals KP, or G complement has an edge. Right? Those are contrapositive statements, right? That G equals KP or G complement has an edge. Or I should say, this is the bare negation of that, not contrapositive. G complement has an edge is the bare negation of G is the complete graph on P variables. Well, if G is the complete graph on P variables, then it contains this complete subgraph on P variables. If it is not, then G complement has an edge, which is the same as having a subgraph, which is K2. So that is the quick proof of RP2 is less than or equal to P. The proof for RP2 is greater than or equal to P is not hard. Remember, it's same as we did here for Z5. You just want to find a G, one specific counterexample to show that not every graph on P minus 1 vertices has the P2 property. I found on MIT, I've referred to this a few times in the past. These are freely available lectures online. I'm going to share that screen with you here real quick. Let's see. So if you, I didn't post a link to Canvas. I almost got there this morning and didn't make it. But if you Google Jacob Fox Mat 307, you will get a link to all of his combinatorics lectures. And they're presented in such a way that is pretty accessible still. We have the same starting point here in proposition 1. Like I said, that is kind of the seminal problem. You have a definition here, a couple of definitions about clique numbers. Here's a definition of Ramsey numbers. All of this corresponds in terms of what we did. Now, theorem 1 is interesting because, I don't want to highlight all of that. Theorem 1 is interesting because Ramsey, the mathematician that developed this field, his original theory is just that there does exist an integer for each of these cases. In other words, that RST is finite. This particular bound that this author is given is the more recent bound. It's not the original bound that Ramsey gave, but it's based off of this inequality here, the one on this line. So if you look at this inequality, you see that it's related to the idea of a binomial coefficient. We have a certain triangle inequality instead of a triangle equality. And that is, this whole theorem can be proven using a combinatorial argument in these two bullets, which is pretty cool. So the idea here is that the next Ramsey number, the Ramsey number ST, is dependent on the one that comes before it in the S direction and the one that comes before it in the T direction. And essentially what we're doing is we're talking about, well, how many independent sets and how many cliques could have existed in those two. And this is how we could form it. And this actually gives us the Ramsey 4-4 number has to be less than or equal to 18. That's the last one for which this bound is good. So according to this, the Ramsey 4-4 number has to be less than or equal to the Ramsey 3-4 number plus the Ramsey 4-3 number. Let me pop back over to the table here. And so the 3-4 number and the 4-3 number are both 9 because they're symmetric. It doesn't matter which order you put a Ramsey number in. And so the Ramsey 4-4 number we know is 18, but from that inequality we know that it has to be less than or equal to 9 plus 9. If we wanted to do the same for the 5-5 number, we would need the 5-4 number, which is 25. And so all we would get there is that the Ramsey 5-5 number is less than or equal to 50, which we already know. So after a while, I mean, that would give us this upper bound, but the upper bound here is 48. We've already beat the 50. Some of these down here may be just the upper bounds, and maybe not exactly this one, but it may just involve the upper bounds here. If we said it's less than or equal to 12,677 times 2, that doesn't come out quite right. We must be using a slightly better bound than that. But that's why this talks about non-trivial values in bounds, because some of the bounds are trivial. They're known just kind of based on these elementary inequalities. Let me go back to the other page real quick. Where'd it go? There we are. So this inequality is sort of the first inequality that you should develop if you're working on Ramsey numbers. And when you put it together, the second half of this proof is really kind of neat because it's super accessible. If we assume that this holds for, we know this holds if we plug in something small like S and T equal 1. And then the rest is a proof by induction. and proof by inductions with binomial coefficients are usually pretty straightforward. I mean, sometimes they take a page of algebra, but they are usually pretty straightforward. So I think that's really kind of a neat proof. And specifically, if we look at this bound here for the symmetric numbers, that's really ugly. I'm sorry, I keep highlighting it weird. If we look at this for the symmetric Ramsey numbers, like the 5, 5 case, then we'd see this is 5 plus 5 minus 2, 8, choose 4, which I don't know off the top of my head. Anybody know 8, choose 4 off the top of their head, or punch it in real quick? I don't have a calculator open, or else I would punch it in. $28. Oh, 8, choose 4, sorry. Yeah, 28 would be, that would be a breakthrough in Ramsey theory. 70. So, ooh, that is not as useful as it could be then, is it? Because we already know the Ramsey 5, 5 number is less than or equal to 48. And so 70 is an example there of a trivial bound. And we might have trivial bounds for, say, the Ramsey 25, 25 number. So I mentioned that one of the ways that we have made the Ramsey numbers easier is to look at what happens if I do more than just a 2 coloring of my graph. If we talk like that, then we can't talk about the graph and its complement anymore, which is fine. We talk about it in terms of, you know, how many, what if I color the edges in 4 colors, then where is my order out of chaos there? The examples of the applications of Ramsey theory in our book talk about noise reduction and some other things, but our book is, quite frankly, a little bit old. There are some applications to networking, and specifically like social networking, and I don't quite have all the answers, because mainly I mess around with it because I think it's fun. I wanted to point out to you, you guys are familiar with Paul Erdős, right? The Hungarian mathematician, and the Erdős number and all of that. So he was talking one day about the Ramsey numbers, and because of how difficult they are to compute, let me pop that up again. This table is nice to just kind of ponder. So he was talking about the 5, 5 versus the 6, 6 case. These are the 2 smallest symmetric cases that aren't known. Notice that we have some pretty decent information for like the 3 whatever case, and the 2 whatever case is not on here because that's a trivial thing that we know. Like I said, if it's a homework problem in your textbook, then it's not really, hopefully anyway, an open theory and graph theory, or an open problem in graph theory. But for 5, 5, he said once, imagine an alien force vastly more powerful than us, demanding the value of R5, 5, or they will destroy our planet. In that case, we should marshal all our computers and all our mathematicians and attempt to find the value. But suppose instead they ask for R66. Then we should attempt to destroy the aliens. Admittedly, he said that at least 20 years ago. So at some point we'll move the needle a little bit, right? And we'll have, yep. We'll have, yeah, I suppose they are symmetric. So our book calls that out as a special case. But it's really just the same as this one. All Ramsey numbers are symmetric because if you are doing the 3, 4 property, and so either your graph contains a blue triangle, or your complement contains a red K4, then if we were looking for the 4-3 number, well, then this would be our graph and that would be our complement. And so we have symmetry. It's fairly widely believed that 43 is the 5-5 number because we have been attacking it for the last 10 years or so with computers, and we have not found a graph on 43 nodes that lacks that property. But that's not a proof. You know, we just haven't gone through all the cases yet. Some people get annoyed by proofs that use computers to just check all the cases. I think it's just a matter of degree. I mean, we very often check all the cases when we're proving things, right? We did that here for R66. We checked all the cases for a graph on 6 vertices. We just were able to do it with a marker on paper instead of a computer. So to tut when you've checked all the cases, I don't think that's a reasonable argument. Now, you can say that it lacks. Yeah, that's exactly right. When there aren't many cases, nobody thinks it's a big deal. But when there are a lot of cases, people think that it lacks elegance, and some people go so far as to say that it isn't even really a proof. I saw that complaint on Twitter, the math Twitter the other day about, you know, somebody was like asking the question, what is the ugliest proof you've ever seen? And somebody was complaining about the proof of the 4-color theorem. And I don't know. I think that it all comes down to human ingenuity. And if we've managed to be clever enough to be able to check all of the cases, then we've managed to be clever enough to check all of the cases. And that's just another way to do it. The last thing I wanted to close is why this is so hard. And so this, I actually just Googled this morning. I forget exactly what I was Googling for, but this popped up and it seemed like a worthwhile thing to share. Let me share the screen one more time. So this is from Math Stack Exchange. Let me make it a little larger. That didn't work. All right, anyway, it says, why are there so few known exact Ramsey numbers? And this part right here is nice. So R55, 43 is the current lower bound. So the graph has 903 edges, and so there are 2 to the 903 possible colorings, which is the same as saying that there are 2 to the 903 possible graphs to check, graphs and their complement. So it's the same whichever way you do. This is a 272 digit number. Goes on to talk about how there are more, that number is larger than the number of protons, neutrons, and electrons in the entire observable universe. I did not verify that claim, but it is a large number indeed. And the upper bounds, there is some work on lower bounds that involves a probabilistic method. Some of these things haven't improved in like 50 years. We're still using the same thing that Erdős found 50 years ago. And the current upper bound grows at a rate of an exponential rate with a growth factor of 4. It says it's been improved a bit, so that's better than what the number we just pulled out of that other lecture, which matches this one. But generally it's the same. It's just as bad or almost as bad. So oh, that's what happened. Um, so when we look at this, when we look at Ramsey numbers, the work to be done is on ways to be more clever in how we pursue this. I mean, we could honestly just build a better supercomputer, and we could probably, if we dedicated a lot of resources to it, um, you know, for the small price of a few $1,000,000, we could probably build a sufficient supercomputer complex that would crank out R55 within a couple of years, and we could publish our process and take pictures and be published in the various journals and things. And but that wouldn't necessarily help us with R66 or any of the others. And so a lot of the work that goes in here is into how do we guess these things cleverly? Is there a way to narrow down the number of things we have to check? Is there an approximation method, such as has been used to approximate the traveling salesman problem? That would be an amazing thing. So anyway, Ramsey theory is one of these fields that is kind of ripe for the picking. The introduction to it is accessible to an undergraduate student. If you want links to any of the things I pointed at today, if I flipped through them too quickly, I can get them to you. Um, and you don't have to blow the whole field wide open to publish. If you can create an edge case, or what some people have done is they've done Ramsey numbers for cycles that turned out to be fairly easy, or line graphs or wheel graphs or other well-known trees, well-known graphs like that, then those things turned out to be easier when we're not dealing with complete subgraphs. So anyway, I've kept you guys too long. That is your introduction to Ramsey theory. I'll give you something a little bit more to chew on Friday. I'm going to stop recording. See